This is chapter 3, section 1, and this is the third video. Electronic structure and properties of the elements is what we are discussing, and I am Dr. Sandi. As we said in the last video, we're going to go over just a couple of examples or questions or problems in this one. The first one we have here, and what I want you to do is I want you to pause if you want and try to answer the questions. We will not have the answers as part of this video, and that is to force you to work on them instead of just moving forward without doing any work and looking at the answers. So which line or lines represent the amplitude here? Remember, we symbolize amplitude with the letter capital A. We have line A, B, C, D, and we have a label E here. Second question, which options represent a wavelength? We have the same 5 letters from before, and now we have the horizontal distance between point 2 and 3. This distance, horizontal distance between point 2 and 4, this distance, and between 3 and 4, that would be this distance here. Which options represent a wavelength? Which one has greater wavelength, amplitude, and higher frequency, wave A or B? And from this one here, I would hope that you can tell what the relationship between frequency and wavelength is. If you look at this diagram, what happens to the frequency as the wavelength goes up? Or what happens to the wavelength as the frequency goes down, for instance? What type of relationship is observable from this diagram? And I have the answer to that very last question. We have a relationship here. We have an equation that relates lambda, the wavelength, with nu, the frequency. And as you can see from this equation, they're inversely proportional. If we solve this equation for the speed of light, c, we see that the product of wavelength times frequency is a constant, the speed of light. So for this constant to remain constant, if we increase the wavelength, frequency has to go down. If we increase frequency, wavelength has to go down. What is the same, what is different for these 3 waves? And one thing that I want to tell you that I didn't do before is that when we talk about amplitude, for instance, if we have sound waves and we talk about amplitude, we are referring to the volume. So a high amplitude would be high volume. When we talk about visible waves, there's a tendency to misinterpret the idea of amplitude, and quite often we associate higher amplitude with more energy. We will see that is not the case. When we have higher amplitude, what we have is a ray that is brighter. So it relates to brightness and not to energy. We will see that what happens is that we have more, if you want to think about it this way, for the time being, we have more rays of the same energy, and thus we have light that's brighter. But each individual ray would be of the same energy. So the energy of the radiation would be the same, the brightness would change. And we compare these others here in terms of energy, frequency, wavelength, amplitude, and velocity or speed in vacuum. A reminder, the electromagnetic spectrum, we're familiar with it. Visible light is just a small portion of the spectrum. intuitively or from experience, we know that different radiations have different energy. We know that gamma rays are higher in energy than radio waves, for instance. But now we have a quantitative way to describe that. We can relate the energy of the radiation with its wavelength and its frequency. So we see that the higher the energy of the radiation, the smaller the wavelength. And the units here for wavelength are meters. Since wavelength and frequency are inversely proportional, and I hadn't noticed, I just noticed that they have a lambda here when it should be the letter nu, the Greek letter nu. So you all can fix that. So wavelength and frequency are inversely proportional. So if the smaller the frequency, the smaller the wavelength, the higher the energy, then we have that the higher the frequency, the higher the energy, because frequency and wavelength are again inversely proportional. And one of the things we need to remember clearly is that there is this that we associate different energies with different wavelengths. Okay, it doesn't have anything to do with the amplitude. The amplitude would be the brightness. So we can have light of a given color that is very bright or not so bright, but the energy of the radiation would be the same. And with this, we're ready to talk a little bit more about the three phenomena that I mentioned at the beginning of this video, or the one before, that were not explainable by classical mechanics, and that gave rise to a quantum mechanical model. And those are the ultraviolet catastrophe, the photoelectric effect, and the emission spectra of elements. And we're going to discuss that in the next video.